Are you ready?
Good morning, sir.
Morning, Mr. Brown.
Could you please introduce yourself to the jury and spell your first and last name for the court reporter who's next to you?
Absolutely. My name is Judson Welcher. My first name is Judson. Last name is Welcher, Welcher.
Sir, what do you do for a profession?
I'm an accident reconstructionist and biomechanical engineer.
I'd like you to explain to us a little bit about what an accident reconstructionist does.
Sure. You can think of accident reconstruction and things such as this as the physics and engineering that happens in car crashes. So accident reconstruction tends to deal with everything that happens to the car and outside the car, skid marks, vehicle damage, the electronic recording systems in the vehicle, things that have to do with the motion forces and how the physics of everything occurred and how that affected the motion of the vehicles.
You said that you were an accident reconstructionist, but also a biomechanical engineer. How is your work as a biomechanical engineer different than an accident reconstructionist?
So simply, you can think of biomechanics as similar, but to everything inside the car. So biomechanics is looking at how the effects of physical forces are applied to the human anatomy. When I'm trying to explain to somebody what I do, I say, hey, it's like a civil engineer who's designing a bridge. So many trucks and cars on the bridge. Are that going to cause the beams in the bridge to fail? Is that going to cause the cables to fail? So a human body is governed by the same laws of physics, just like the bridge. Obviously, it's made of a lot of different materials, but in a human body, my beams are bones. My cables are the muscles and ligaments. Different material properties, but everything's governed by the laws of physics and principles of engineering. So I'm looking at how physical forces, the outside of the car, when people are inside the car, seat belts, airbags. The first seat belt was patented by an engineer. It's engineers who quantify the force of the crash and what kind of injury damage there is to the body. So it is force that causes damage like a fracture. And so we're looking at how the physical forces are applied to the body and what that means in terms of what happens to the body.
Dr. Welcher, I want to ask you a little bit about how you became a biomechanical engineer and an accident reconstructionist. Can you tell us?
Sure. So when I was getting ready to go to college, my father, who was a physician, said, whatever you do, do not go to medical school. Because I was getting ready to go to medical school. So this was 39 years ago, I believe. 35 years ago, 39 years ago. He said, it's just not worth it. So I said, okay. So then I entered into the mechanical engineering. I grew up riding motorcycles, taking things apart, frequently pissing my parents off when I couldn't put it back together. But I liked taking things apart and figuring out how things worked. So I went to university and got my undergraduate degree in mechanical engineering. From there, I happened to be at a Thursday meeting of the American Society of Mechanical Engineers. A group came in from a company that did this type of work, and they showed some examples of how you apply engineering concepts that you learn in mechanical engineering to the human body. And so I was like, man, that's a great job. That's the perfect mix of engineering that I have and my desire, to learn the medical side of things as well without becoming a doctor. So I talked to them. I actually applied to the company and was ultimately hired as a biomechanical engineer.
How long did you continue as a biomechanical engineer until you went back to school?
So I actually, very quickly after I started the job, I took a human anatomy class at a community college. I quickly realized that wasn't enough. And so in around 1993, I went to the USC Medical School and enrolled through what's called concurrent enrollment, which means you can take the class, but you're not actually in medical school. It's a medical school class. But I took gross human anatomy. So it was me and 160 or so other doctors. I took the same human anatomy that first year medical students at USC took. So it began in 1993.
Did you continue to work as you pursued your higher education?
I ultimately started my own company, continued to work, continued to do research. I had a wonderful opportunity to have two beautiful children. and continue to this day.
Tell us a little bit about the company you started and when.
Sure. So in about October of 1994, I started my own company. Me and the guy who was my immediate supervisor said, hey, we can do this better. We can do more research, more testing. And so we started our own company.
What kind of company was it?
It was an accident reconstruction and biomechanical engineering company. We also early on did a bunch of testing and design work for amusement park rides. The same concepts for car crashes applies to roller coasters, basically anything. So we worked and had some contracts on improving ride safety. And I was also on the ASTM committee that looked at amusement park ride designs.
Did that company grow from 2 people?
Correct. We took it from 2 to about 25 people, and then we ultimately sold it in right around January 1st of 2022.
Before 2022, did you obtain a master's degree?
I did.
And what was that in and where was that from?
So again, I was working full time. Actually, while I was doing my master's degree, I was also teaching classes at Texas A&M through their law enforcement training division. So it was extension classes. But I ultimately completed my master's thesis in December of 2001. That was from USC, University of Southern California. And I received my master's degree in biomedical engineering. I wrote my thesis. It was basically on automotive seat design, but it was titled Whiplash-Associated Disorders, Related Anatomy, Biomechanics of Injury, and the relationship between injury potential and automotive seat design.
Excuse me, Robert, if I may, pardon the interruption. If Dr. Welcher reads from his report, which I think he just did, should we know that he's reading?
Sure. Dr. Welcher asked me if he could refer to his resume, and I said yes. So if you read, just let us know.
And it's my resume, not my report.
Your resume, did I say report?
No, you did. He said report.
Yeah, no, it's his resume.
You share with us that your company continued to grow until you ultimately sold it in 2022. During that time, did you continue to pursue higher education after you obtained your master's degree?
I did. So again, ever since 1993, I've been slowly pursuing higher education, both obtaining my master's degree as well as my PhD. During that time frame, I also published 20 peer-reviewed scientific publications. I taught for 5 years at Texas A&M and served as a peer reviewer for both the Society of Automotive Engineers and for a short period on the Archives of Physical Medicine. So I was working and running a company with my co-creator, as well as teaching, conducting research, publishing, also while going to school part-time.
Take us to 2011. Were you still pursuing education at the University of Southern California?
I was.
And what occurred? What did you achieve in 2011?
So in August of 2011, I finally obtained my PhD in biomedical engineering. I wrote my dissertation, reading from my resume, titled Development, Validation, and Testing of a New Sensor Array for Intra-Articular Pressure Measurement, In Vitro Human Lumbar Spine, Intra-Articular Facet Testing, which is a lot of big words to say. I was testing cadaver spines, looking at the loads inside the spines associated with various motions of the spine.
Did you achieve your PhD in biomechanical engineering?
It's actually in biomedical engineering. Biomechanics is within the field of biomedical engineering.
So you have a PhD in biomedical engineering.
Correct.
You mentioned that you've published many articles. Have there been articles that you've published that are relevant to some of the subjects that you're going to talk about during your testimony?
I mean, I have a number of, again, peer-reviewed scientific publications. Peer review just means you submit it to a journal and they have other people review it, give you comments, your peers in the field. I do believe there are a number of them that could certainly be relevant to both the physics and, for example, pedestrian injuries.
If I could mention a few. You wrote an article on sideswipe collision dynamics. What's sideswipe collision dynamics?
So I was actually an invited speaker at the World Congress, sorry, not the World Congress, the World Reconstruction Expedition. they asked me to give a presentation on the theory, science, and mathematics behind side swipe or side impact collisions. That would include side collisions, glancing collisions, shallow angle impacts such as like a corner of a bumper goes into the side of a car, any kind of glancing or clipping type impact.
Similarly, in many of the articles that you wrote, is one of them about methods for quantifying the impact severity of low-speed side impacts at varying angles?
It is.
Can you tell us a little bit what that
So that was a Society of Automotive Engineers paper, again, another peer-reviewed paper that we worked on. It was kind of an extension or continuation of all that research, where we just looked at the physics and the mathematics, basically the reconstruction of glancing or side swipe type impacts.
Similarly, methods for quantifying the impact severity of low-speed side impacts at varying angles. Is that similar to the other papers, or was that different?
Yeah, I thought that was the same one.
If I can continue, another article or publication that you wrote, occupant kinematics and loading in low-speed lateral impacts. What does that mean?
So in the course of my career, I've done probably 12 to maybe 1,300 actual crash tests. I've crashed everything from skateboards, mopeds, up to trains, motorhomes, and ambulances. I've conducted, relative to this case, probably or been involved with 50 to maybe 70 pedestrian impact tests. So the low-speed side impact one is we actually put human volunteers in side impact collisions. And what we did is we had accelerometers, which are things that measure acceleration. If you had physics or memory, Newton told us force equals mass times acceleration. So knowing the acceleration of something, you can get an idea of how much force is applied to it. So we have various sensors on the body. We have various sensors on the car for the reconstruction aspects of it. So that study was the biomechanics portion. And the first paper you read about the reconstruction was the reconstruction portion. So the first paper you discussed was everything outside the car. Then we looked at how the forces applied to those impacts to people inside the car.
Have you had a lot of publications and studies about the force applied to people outside of a car?
I don't know if I'd say a lot, but I was an invited lecturer to the Action Reconstruction and Collision Safety Institute conference, where I specifically gave a paper and a series, or basically a lecture on what's called pedestrian impact biomechanics, which was exactly as the name implies, and, what happens to pedestrians when they're impacted predominantly by cars and vehicles.
How much of your work involves pedestrian impacts?
Probably maybe 10%, 5 to 10%. Most of it's car to cars.
Biomechanics of low-speed impacts. Is that another paper that you wrote?
That is a paper I wrote.
I don't want to read all of your papers and all of your publications, but on a different topic, did you write a paper on the study of the measurement of Generation 2 Toyota event data recorders and low-speed side impacts?
Yes.
Could you tell us a little bit about what measurement of event data means in this?
So, Toyotas, newer Toyotas particularly, have two types of electronic equipment on board that can record crashes. There's what's referred to as an event data recorder, or EDR. It's somewhat commonly referred to as a black box. It's not exactly right, but it's close. And then there's a secondary system, which is really more closely tied to maintenance. That's called TechStream, but it will pick up data that you can frequently relate back to various events. So that particular paper was looking at the event data recorder data in Toyotas.
We'll get more into that subject later, but is event data recorders a subject that you're well schooled at?
Yes.
In addition to the papers that you've written, have you continued through the years and after becoming a PhD, your research in this area, in these areas?
Correct. For example, every year we're part of a conference called SATI, which is our company, largely led by an engineer, Christopher Furbus, that we work with, has spearheaded us going out and conducting crash tests for that conference for 10 years. We did a lot of the instrumentation and crash testing at the Accident Reconstruction and Collision Safety Institute conference. And then for a number of years, I actually, the company actually went down and did crash testing for what's referred to as the Spine Research Institute down in San Diego. So we've been hired by various professional organizations. We came out here once, the Massachusetts Association of Action Reconstructionists, I think I'm messing the name up, had a conference. We came out here and conducted crash tests for training other experts out here. We did all the instrumentation, the biomechanics of that crash testing.
In your research and testing, you have pages with dates of the different researches and testing you've done. There's over a dozen of the research and testing items and articles that deal with pedestrians. Is that a common topic in your research and testing?
Yes. So again, frequently at the conference, we're doing pedestrian tests. The last Action Reconstruction Collision Safety Institute conference, there was a series of pedestrian crash tests run there. SATI 2 years ago, maybe 3 years ago, some pedestrian crash tests that were done there as well. So there are a number of instances on my resume where I have both attended class, and then I mentioned the one time where I gave an hour and a half long lecture on pedestrian injuries.
After you became a PhD or a doctor, do you continue your education and research?
Correct. I've always continued my education and research up until, I just got back from the event data or Action Reconstruction Collision Safety Institute EDR conference, or the Event Data Recorder Summit. My company, through my relationship with the founder of that summit, was a sponsor. So Aperture was actually a sponsor of that conference. We actually sponsored it the previous year as well. And also as part of that, I assisted one of the researchers in conducting, it's called front camera module testing for pedestrian impacts on Chrysler vehicles. General Motors vehicles.
As a biomedical engineer, are there any groups, organizations, or certifications that are important?
I think ACTAR is important. So ACTAR is an acronym. It's ACTAR, and that's short for the Accreditation Commission for Traffic Accident Reconstructionists. And so it's a bunch of professional groups, originally from some concerns, I believe, from the Department of Transportation, got together and set standards for reconstructionists. Again, these are kind of minimum standards. You have to show, you send in your resume, you talk to them about your research, and then if you're deemed qualified, you sit for an examination that tests your skills, day-long test, theory, a practical portion, and then every 5 years you have to have 60 continuing education units to become reaccredited. I've been an accredited Action Reconstructionist since February of 1995, and my accreditation is current and active up through today.
So you've been accredited for 30 years?
Yeah, correct.
I don't want to trick you on the math.
No, I never thought about it, but yeah, I guess it has been 30 years.
Have you testified in court before?
I have.
Have you testified in state courts?
I have.
Have you testified in federal court?
I have. Matter of fact, in Boston.
Have you ever testified in civil cases?
Yes, I have.
Have you testified being called by the plaintiff?
I have.
Have you ever testified being called by a defendant in a civil case?
Yes.
Have you testified in criminal cases?
I have.
Have you ever been called by the state or the government?
Yes.
Have you ever been called by a defendant?
Correct. Public Defender's Office.
In any of the cases, whether it's civil, criminal, plaintiff, defendant, government defendant, does that in any way change your analysis about data regardless of who or where you testify?
No. I take my job as to be a critical analysis of the data. So I wanted to look at the data as objectively as possible and form conclusions based upon the data, trying to remove wherever possible speculation, try to remove wherever possible reference to testimony. Now, sometimes testimony is the only thing we have, and so we need to rely on it for bits and pieces. But generally, my job is to try and look at data and see what the data shows. I have no dog in this fight. I don't, quite frankly, care. What I'm doing is trying to do a good engineering job, which is looking at the data and drawing sound principles and sound conclusions from the data.
Presently, you said you had a company and you sold it. Where do you work?
It's a company called Aperture. I guess we were acquired or merged into it technically.
How many offices do you know Aperture has?
Oh God, I should know that. I mean, we have them in Massachusetts. We have them in, I think there's 3 or 4 in Texas. There's, I think, 4 or 5 in California. So I want to say there's at least, I don't know, 13 to 15.
Do you work at a particular location?
I do.
Where do you work?
Long Beach, California.
Do you work with other people? Do you have a team?
I do.
How many people are on your team?
5.
And what's the team comprised of? Is everybody a PhD, an engineer?
One individual is a PhD in engineering, Dr. Umali, and then I have 3 other engineers and 1 case reader. I guess it's 6 people. I have a case manager as well.
Is there any, do you work interchangeably at the different branches around the country, or do you have your own team in California that you work with?
99% of the time, it's my own team. Occasionally, we'll get a case from another office. I've worked on a couple cases out of the Texas office and maybe a couple out of the Nevada office.
Were you asked to look at any data or information relative to this case?
Yes.
In looking at data and information, do you try to look at a narrow or broad range of information?
So I definitely cast a very broad range. We try and get as much information as possible, and then weed it down to what is important, weed it down to what is consistent with the data. So start off very big, and then get down to sort of the meat and potatoes of it, the important information.
Do you necessarily rely on everything you look at?
No, I certainly consider everything I look at, but I frequently don't rely on everything because sometimes it's not reliable or it's irrelevant.
In this case, can you share with us materials generally that you looked at in your review?
Sure. Your Honor, may I read from my report?
Yes.
Thank you. So, Mr. Reporter, I apologize. It's a lengthy list. Slow? So I have police reports, including the Canton PD incident report, and I have 8 other reports, also the 34 Fairview Road Rams final report, or CARS report. I have the ring video from Mr. O'Keefe's residence. I believe that's One Meadows. I have the cruiser cameras, which are the police vehicles, onboard cameras, both front and rear cameras from 1, 2, 3, 4, 6. I believe 10 different videos. I have photos and videos of the scene from Sergeant. I have photos of the vehicles, 140 photographs of the vehicles lined up together. I have 25 additional photographs of the scene, 18 separate photographs of the scene, 2 photographs of the scene, 1 group of 92 of the scene, 1 group of 50 of the scene, another video showing the cars lined up bumper to bumper, 4 videos of the scene. I have a video showing Miss Reed's vehicle being pulled into the Sally Port at the Canton Police Department. I have a 360 diagram, surveillance video files from McCarthy's, surveillance video files from Waterfall Bar, Canton Police Report, Sally Port videos from Dighton, I have the Lexus Connect Verizon records. I have the alarm.com videos. I have a video of the tow truck arriving at the Canton Police Department. One titled Native Location, John O'Keefe's Phone. House witness statements. The report of examination from the coroner. Jennifer McCabe Cellbrite data. Something called Lexus Infotainment. Different PACS summary, testimony of numerous witnesses. An earlier summary testimony of numerous witnesses. The Boston Magazine interview with Miss Reed, a Dateline interview with Miss Reed, a 2020 interview with Miss Reed, lab reports from BODE, the Crime Scene Response Unit Boston, Crime Scene Service Section Maynard, Crime Scene Service Section Southeast, the Criminalist File Folder, Trace File Folder, UC Davis Veterinary Report. I have Verizon records, GPS location records, John O'Keefe GPS points, Axiom cache location, weather reports, medical records, including the Canton Fire Department run report for both Mr. O'Keefe and Miss Reed, medical records for both Mr. O'Keefe and Miss Reed from Good Samaritan. I have 2 retrograde extrapolation reports, one, and a serum plasma conversion report relative to Miss Reed. I have the neuropathology report. I have the Orange County Medical Examiner's report, the diagrams, the postmortem toxicology report, and a second same autopsy report, more pages.
In addition to the information that you reviewed, did you on your own go out and obtain information that you thought might be helpful for your review?
I did. So first what happened is I asked for all the information on the case. So I received some information, and then what we do is we start doing our homework. So we start doing the groundwork. So once I received some of the information, what I did was, modern cars have what's called a VIN number or vehicle identification number. It's a unique 17-digit number. So what we'll do is we'll decode that VIN number, and that gives us information about the vehicles. So I did that for Miss Reed's 2021 Lexus, as well as Mr. O'Keefe's 2019 Chevy Traverse. So ran the VIN numbers, use the VIN numbers. It tells us year, make, model, safety equipment, things like that. I then got dimensional data from a program called Expert Autostats. And then I have complete parts diagrams for the vehicles. So I have literally bumper-to-bumper parts diagrams from something called the Mitchell Collision Estimating Guide. And what that is it shows parts, involved in the vehicle. So for example, in Miss Reed's vehicle, I have bumper-to-bumper. I certainly have all the parts around the rear bumper and tail light of her vehicle. And then, of course, I started additional work on top of that.
After you began your study, sir, did you have an opportunity to personally look at items that were involved in this case?
Yes, I did.
And what did that include?
That included looking at Miss Reed's vehicle, looking at Mr. O'Keefe's vehicle, going to the scene of the incident. I ultimately purchased a 2021 LX 570, the exact year, make, and model of Miss Reed's vehicle, and conducted testing with that vehicle, as well as doing a whole bunch of research and compiling data for my report and slides.
You mentioned slides. When you went through your investigation analysis and ultimately led to whatever conclusions you have, did you provide and create a PowerPoint presentation that could assist you?
I did. I provided a PowerPoint presentation on January 30th.
May I approach, Your Honor?
Yes.
Yeah.
Yes.
So I'm handing you a binder. Would you kindly take a look at it?
Okay.
So does that appear to be a copy of the PowerPoint presentation that you prepared for us to go?
It appeared, right? 141 pages. Didn't look at every page, but it looks right.
All right, I asked to mark this for identification.
Okay.
With the court's permission, I'd like to have Dr. Welcher use his PowerPoint presentation to walk us through some of the information he'd like to share today.
No objection, Mr. Lessing, right?
No objection, Your Honor, thank you.
Your Honor, I'm looking at a paper version in front of me.
Okay. Is the paper version the same as what we're going to see up here?
It is.
Okay, then that's fine.
Thank you. And Dr. Welcher is going to manage the PowerPoint presentation. So you mentioned that you wanted to look at the area and look at the scene. Your office is in California.
It is.
Why was it important to come all the way out to this area to see the scene firsthand?
Hold on a minute.
I'll let you set up before I start asking you more questions.
So that's me. No, that's my first slide. Again,
I have a couple questions for you, Dr. Welcher.
please.
The first is, your office is in California.
Oh, yes, sir.
Why was it important to come all the way out here and view the scene firsthand?
And you want to have as much information as possible. So I wanted to, physically look at all the things so I can actually see with my own hands, my own eyes, lay hands upon it, look at it as best I can. You try and inspect and look at as many things as you possibly can. Sometimes they don't exist anymore, sometimes they're gone, and you have to make the best approximation if you can't do that. In this case, I was able to look at the scene and both vehicles.
Was that an important part of your study, Doctor?
I think so. Again, it's always good if you're going to talk about what happened to the cars or what happened to the people to look at what happened to the cars, meaning to actually look at the cars, not just look at photographs when possible. So I have physically looked at the cars. For example, on the Lexus, I climbed in it, over it, underneath it. I downloaded data from it. I did a whole bunch of things looking at Ms. Reed's Lexus to assist in my analysis to try and add some further objective data to what we're doing here. So same thing with Mr. O'Keefe's vehicle. Looked at the rear bumper, took some pieces off the rear bumper to see what was behind the cover, to see what kind of damage we did or didn't have. So went to the scene, looked at the measurements of the curb, looked at where some of the lines are on the road because you can see them in some of the photographs. Again, it's always good when possible to inspect everything you can inspect.
If you could now begin and tell us how you started your investigation.
Sure. So on September 23rd, I had an opportunity to come out. Mr. Brannon, was the first time I ever met you on that day, I believe. And I had received material before that. And what you see here is, this is my inspection of Miss Reed's vehicle. In the upper left photograph, you'll see, oh, this doesn't work very well. Upper left photograph, that's Miss Reed's vehicle, that's Mr. O'Keefe's vehicle, the Chevy Traverse. And then what you see here is a laser scanner. You can see it on the ground here. Laser scanner is creating a 3D model of the vehicles. So I used that to create a 3D model of the vehicles. You can see me in the upper right photograph. That watch is this watch right here, my Garmin watch. And what I'm doing is looking at the construction composition of that right rear corner of the bumper. I'm looking at things such as the dimensions, where various lights and components are, and how does the geometry of that bumper relate to things that would be hit when backed into.
Dr. Welcher notes this is 9/23/94. Is that an accurate date of when you came and first started looking at the vehicles in the area?
You said 24, correct?
I did.
You said 9/23/24, correct. And then on the slide, what I tried to do is underline what I'm doing. So this is inspection of the Reed Lexus. And as noted, I'm only showing you a couple. I actually took 445 photographs.
Do you remember when you began this case? The month or the date?
No, it was obviously before this. I had material before I came out to look at the vehicles.
You think it was months before this?
I don't think it was months. No, it was maybe a month, if not less.
So you began your work in the fall of 2024?
Correct.
And I just want to ask you about the picture in the middle. You see the right taillight housing is missing. Did you
Correct.
understand that had been removed prior to you looking at the car?
It was, yes.
Thank you.
You're welcome. However, some of the evidence stickers, these white stickers here, were still on the vehicle.
You did not place those. Did you place those stickers on yourself?
I did not.
Were they there when you first saw the car?
Correct. They match what I'd seen in other photos.
Thank you.
So just continuing on, so what you see is, again, I mentioned looking underneath the bumper. So we wanted to see what, if anything, was damaged on the corner. So I'm putting my hand to show where the frame rail ends. This is me looking up underneath to the back side of this taillight. If you can see, this red taillight actually sticks out. And so I'm checking the front here for damage. I'm checking the back for damage.
1 second, please. Okay, Doctor, when you were looking for damage on the previous slide, did you find any damage to that lower right red taillight?
No, there was no damage to the taillight.
The middle picture is from the inside, looking at the inside of that taillight. Was there any damage to the inside of that taillight?
There was not.
Thank you.
You're welcome. So again, looked at the height of it. I mentioned this lower taillight. Notice how the structure of the bumper protrudes out. You can see one of the marks, which is consistent with the contact in Mr. O'Keefe's vehicle. Here, this scratch mark, or scuff mark. Notice how close it is to this light. Again, some of the evidence, stickers. Just a better view of those, then going down the side of the vehicle. So with all that information, I mentioned a laser scan. So you move this laser scanner, and each minute and 51 second scan is collecting about 50 million data points. And so you scan all the way around, and then what you do is you merge all that data together. So even though this looks like a poor photograph, what you're seeing is hundreds of millions of photographs, hundreds of millions of points. And so you literally can figure out, if you wanted to know the distance from this lug nut to where the lighter is on the ashtray, you could probably do that to an accuracy of about 2 to 3 millimeters. So really, taking tons and tons of data. So it knows the exact position of every one of these millions of data points, and it knows the color associated with those data points.
Why is that data imaging so important in accident reconstruction?
You want to have an accurate model of the car. So, you probably don't need literally that many points to get an accurate model, but that's just the nature of the way the science is going. Computers are getting better and faster. Scanners are getting faster. So you get an enormous amount of data when you use these scanners nowadays. So then, as indicated on the underline here, I did a CDR. That's a little different than what you heard me say before. CDR is crash data retrieval. So that's the hardware and software that you use to download or actually copy or take an image of, means you're just taking an image off what's on the vehicle, the EDR, which is the event data recorder. So you use the crash data retrieval hardware to download the event data recorder, otherwise commonly known as a black box. So I downloaded the black box from this vehicle, and although you can hardly read it here, again, I mentioned there are 2 systems on this vehicle. This is the CDR system or EDR system. There's also the tech stream. The EDR system, this system is primarily to manage the safety components, protect the occupants of the Lexus. So things like fire the airbag, fire what's called a pretensioner, keep track of the severity of the crash to decide whether we need to fire the airbag. So it's not really designed for pedestrian impacts. So when we downloaded this vehicle, we got what's called a none file. A none file simply means that there's no data there. The system's working properly, we had no fault codes, but for a car hitting a pedestrian to cause a file here, this is really more designed for car-to-car impacts, something that's going to have a significant impact on the occupant of the Lexus. And again, the Lexus is a 6,000-pound vehicle. Mr. O'Keefe's only 216 pounds. So it's not going to register from hitting a pedestrian.
Were you surprised that there was no information about a collision in the EDR?
No, exactly what I expected. Okay, I mentioned the second system. So as underlined up here, this is the tech stream. So this is from Toyota tech stream data. You can see the screens here. There's generally two types of files, what's called a vehicle control history and a PCS file. The PCS file is the, God, I forgot the name of it, the protection system. So I also looked at Mr. O'Keefe's vehicle. PCS is pre-collision system. Looked at Mr. O'Keefe's vehicle, same thing, took a series of photographs, laser scanned it, looked in it, underneath it, behind it. I mentioned taking some of the bumper parts off. So I took this rear cover off here to look at the damage behind the bumper cover. Most cars have what's referred to as a face bar. That's that piece of metal that you see here. And there's a piece of energy absorber here. That's your face bar. So I'm looking to see if there's any damage to that. There was no damage to that.
Before you go forward, I want you to take a couple steps back because I want to ask you some questions to explain
Please.
tech stream data. Could you go back a couple slides, please?
Sure.
You mentioned that in the EDR, which is similar to a black box, there was no information found. And then you mentioned a different system, the tech stream. Can you make it clear for us how these systems are different and where they're stored on a motor vehicle?
Sure. A lot of data is stored in a similar location. The tech stream system was originally designed, according to Toyota, for maintenance issues. It seemed to come about around the same time Toyota was having problems with sudden accelerations or allegations of sudden accelerations. So the tech stream data or vehicle control history will give you information when there's, for example, excessive acceleration or rapid shifting of the vehicles or rapid steering of the steering wheel. So the statements are that that's designed to help the maintenance people, if you come in with a problem with your vehicle, to diagnose what that problem is. It has a lot of utility in accident reconstruction because if you jam on the brakes before a crash, frequently the tech stream data will record the crash.
You mentioned Toyota a number of times. Could you share with us the relationship between Toyota and Lexus?
Sorry, in my mind they're the same thing. Toyota and Lexus obviously a little different, but Lexus is basically made by Toyota. So Toyota and Lexus has the Lexus safety system. Toyota has the Toyota safety systems, which you both read with the tech stream data.
The tech stream data, in this case, does it play an important role in your analysis?
I think so, yes.
The tech stream data, did you independently download that data yourself?
So I independently downloaded it, and then I also ran a test with Ms. Reed's vehicle, and I created a new tech stream file so that I had a stamp in the ignition cycles of what the current ignition cycle was. So I did a sudden acceleration test of the vehicle.
On the Lexus or on the exemplar vehicle?
On her Lexus.
When you did the downloading, why did you do it yourself?
Again, you, whenever possible, want to be the one that does it, make sure it's done correctly, and be able to say, hey, how do I know that's from that vehicle? Well, I know because I was the one who did it. And so if I get it from someone else, then they frequently have to bring that person into court to say the other ones that did it, so then I can use it. So if I do it myself, it eliminates that problem, and then I have no concerns over where it's coming from. So then I know hey, I did it. This is the right car. This is the right program.
You left us at slide 10 when you were inspecting Mr. O'Keefe's car?
Correct. So again, simply a blue arrow indicating that I looked down behind all this stuff, took measurements of it, and then similarly I have a 3D point cloud of Mr. O'Keefe's vehicle. So part of the reason we're making these 3D point clouds, and we'll touch on this further, in addition to the scene, you can then basically put all these things back together in the computer. So instead of having to drive the cars to the scene, for example, or to Mr. O'Keefe's residence, you can take these computer models and additional data and put it back in a computer and reconstruct everything on the computer. So before we had the exact angle of impact, again, this is for looking at when Ms. Reed contacted Mr. O'Keefe's vehicle backing out of Mr. O'Keefe's garage at One Meadows. I lined them up just to generally show the approximate location. A couple things. You notice how, again, this lower portion of the Lexus bumper sticks out. Notice how the side of the Chevrolet slopes in as you get higher up. So this portion sticks out more than this portion. And this is where you would expect any contact damage to occur, assuming there was an impact. So again, looking at the measurements of the height of the vehicle, of course, as you indicated, Mr. Brown, the taillight's gone. And then went to the scene. So same thing, went to the scene, took, again, 297 photographs of the scene, had our people scan it to create a computer model of the scene. So, literally, if you wanted to know the distance from this window to, say, some manhole cover on the road, we have the data to figure that out, down to a couple millimeters.
In addition to going to the scene and doing the digital mapping, you mentioned other review of materials. Did you have an opportunity to review dash cam footage from Canton Police Department police vehicles to see the general location of where Mr. O'Keefe was when first responders were assisting him?
Objection, Your Honor.
So that's just a yes or no?
Yes.
Thank you.
So the text stream download. So this is a screenshot from the text stream download. Keep in mind, this is kind of maintenance software. So we're looking at a number of things in the maintenance software. What we see is, and this is noted in the report too, that when the vehicle gets into the Canton Police Department after this event, you can see the mileage is 12,665 miles. So that shows up in Trooper Paul's report. It shows up in the photographs, and it shows up as matching the mileage in the text stream data, both at triggers 1164 and triggers 1167.
I'd ask you if you can enlarge the data on the right and break down what it actually means, the different columns and the...
My fingers are too fat.
Thank you.
Okay. So what you're looking at is what I called event 1162. If you see anything in blue on these charts, that's information that I added. I typically put my initial, JBW, Judson Blair Welcher, that's me. And so this is referred to as the key cycle trip. So key cycle is simply you turn it on, not necessarily turn the ignition on, turn it on, turn it off. That's one key cycle. So I labeled this one 1162-2 because there's also one that's on the same key cycle that I'm calling 1162-1. The system also records the mileage. So again, this is a maintenance system generally. So what you see is the T here is the trigger, and there's a point. So this time in the text stream data, you could think of it as like a stopwatch. It's when it starts when the car turns on and stops when the car turns off. And then if it sees a triggering event, a T, it records that information. So this is when the trigger happened. So that's 1,142.2 seconds. And so I've converted that to minutes and seconds, because most people don't think in seconds. And so what it also does is once it sees a trigger, it's constantly circling circulating data through the computer. So when it says, okay, we have a trigger, it saves 5 seconds before the trigger and then 5 seconds after the trigger. So the trigger's in the middle, and you have 5 seconds of data before and 5 seconds of data after.
I have a couple of questions for you,
Please.
Dr. Welcher. First, starting with the clock, the time in seconds on the left. You mentioned that begins when the car is turned on. What type of clock is that called?
It's just a continuous clock, meaning it's not a clock like a time clock. It's more like a stopwatch kind of clock.
Has it ever been referred to as a running clock?
It's the same thing. You start the stopwatch, it's running.
Based on the text stream data alone found in that one spot, can you tell from the data in the text stream alone what time the power was turned on?
No, not alone. It simply tells you how long it's been on. It doesn't necessarily immediately tie it back to a clock time. You need additional information.
And so this in and of itself, the text stream data doesn't give you a certain time on a clock, like 1 o'clock or 2:30, anything like that.
No, it simply tells you in this case when the trigger occurred, it's been on for 19 minutes and 2 seconds.
You also mentioned that there's a 10-second window of information this captures, 5 seconds before the T and 5 seconds after the T, the triggering event.
Correct.
Sustained, ask it differently.
That window of 10 seconds, what happens if that doesn't capture the entire event? What if there's something before or after? What does the text stream data do?
So it depends on what the something is. So if there's another trigger, then it will record more data. So you can have 2 triggers that are recording things on the same time window as well, or very close to the same time window. So you need another trigger to keep it going. But in essence, what it does is when it sees a trigger, it saves that 10-second window and then just keeps monitoring things until it sees another trigger.
If the data captures a trigger, it has a 10-second window, and an event continues past that 10 seconds, or past the 5 seconds on either side, and there's no further trigger, do you get any other information from the text stream data?
No. For example, in the trigger event, and say 5 seconds later the vehicle's still moving, well, the data just ends. And it says it's going, 17 miles an hour, for example. It doesn't continue on. We just know that when the trigger ended, it was going 17 miles an hour.
Thank you very much.
Okay. Okay, so we have mileage recorded in this system. So what we're trying to do is use the available data to see if we can determine what event this is, or is this the event, or is this something that could have occurred outside 34 Fairview on the evening of this event. And so one of the things we're utilizing is the mileage. Okay, so 12629 is at the end of event number 2 on the 1162 ignition cycle. When the vehicle ultimately comes into the impound yard, and this is actually before that, comes into the impound yard, it has 12,665 miles. That's a difference, did the math for you here, of 36 miles. Okay, let's consider where that could have come from. So we looked at the various paths and descriptions of where Miss Reed's Lexus was driven after leaving 34 Fairview on the night of this event, up until the time the vehicle ended up at the Canton Police Department. So we used Google Maps. We adjusted for the correct date and time of the year. And then what you also see is we adjusted for the correct time of day. So, although you can't really see that, let me see if I can blow it up. So you can see that's looking at the mileage and time. Again, really didn't use the time, just used the mileage on Saturday, January 29th at around 12 a.m. That, of course, does not take into account the weather.
And what are the addresses? It's hard to see on the top from where to where?
So this is from 34 Fairview to 1 Meadows Avenue, which is Mr. O'Keefe's residence.
And there are other mileage that you have there?
Correct. So we basically ran through the entire path as we understood it. Again, we didn't have complete information. We didn't know the exact roads. We didn't know if turned around, stuff like that. So you're seeing the suggested available paths, and we end up with a range of data. So we go through all the paths, and you can see that this is what we end up at the bottom here, which is very hard to see. So the minimum suggested route is 36 miles, 36.1 technically. We have a range of 37.9 to 39.7, but again, that's right in the range of the 36 miles. So that's a data point that's starting to build our confidence in what is in the text stream data being related to our event.
This is all an effort to match whether or not the 1162 data is relevant to a particular event?
Objection, Your Honor.
Sustain.
Let me ask it this way. Matching all the distances by miles, is this the only way you're trying to determine whether 1162 is the event in front of 34 Fairview Road?
No. So again, these things are all tools. You can't take necessarily one data point in a vacuum. You need to consider the totality of the data, which is what I did. So we mentioned the continuous clock that was in there, or the running clock that was in the vehicle. So what you see over here.
Could you arrange that for us, Doctor?
I am doing that right now. You can see we have the time, and again, I've converted it in blue to minutes and seconds. This is the first trigger on that key cycle. So on key cycle 1162, there was 2 separate events. The vehicle keeps a continuously running clock. So we're able to see the time each event occurred relative to when the vehicle was started and the difference between the 2 events. Okay. So at trigger event 1162-1, we know that the ignition has been on for between 10 minutes and 57.4 seconds. Or that's when the trigger is, sorry, 10 minutes, 57.4 seconds. Again, the trigger has plus or minus. So that's from 10 minutes, 52.8, plus 10 seconds, which gets you to 11 minutes, 2.8 seconds. Or, as I wrote here, 10 seconds total. So again, the text stream data indicates at the time this event was written, the trigger occurred, again, at 10 minutes. You see we have the T, 10 minutes, 57.4 seconds.
Dr. Welcher, if I could ask you a couple of background questions. This block of time that you're reviewing that mentions 2 triggers, can you tell whether those triggers are immediately related or 2 separate events?
So you can tell they're separate events because there's a separate amount of time between them. There's about 8 minutes between the events. And so they're on the same ignition cycle, meaning the vehicle hasn't been turned off in between. And we have this continuously running clock that records when these things occurred. So it tells us when event 1 occurred, when event 2 occurred. We know it's on the same ignition cycle. So if we have some idea when the car was turned on, we can then tie that back to clock time or real world time. Okay. So lots going on here, right? A lot to digest. This is trigger event 1162.1. I was provided with data and a report from Mr. Burgess that indicated the infotainment system was turned on at 12:36. That corresponded to a GPS location that looked like it was outside the Waterfall Grill on Washington Street. So additional cell phone data that we had is that we knew there was a 3-point turn made when the Lexus passed Fairview on Cedar Crest, pulled into a driveway, and made a 3-point turn. So what you see over here is GPS data from Mr. O'Keefe's phone. And with that information and knowing when the system turned on, we're able to now tie the text stream data to a real clock, meaning what time of day did that text stream trigger occur. So we're going from the running clock to a real world clock. So if you take when it was turned on for Mr. Burgess's report, you can see that the Lexus was turned on at 12:12:36. You add in the text stream information, you get it at 12:23:38. And now we have a cell phone data point at 1:54. So at the time my report was written and these slides back in January, that was all the information we had in terms of data point 154. That was the one that was closest in time to it. So we had since received additional information.
Dr. Welcher, let me ask you a couple questions, and if you can zoom in a little, we might be able to see it a little better from here.
Where would you like it?
If we can start at the top when you explain in text. You told us that the text stream data does not have an actual clock, it has a running clock, like a stopwatch.
Correct.
And then you mentioned that after you received information from Mr. Burgess, you could put an actual time onto it. How do you do that?
Sustained.
You shared with us that the text stream data runs on a running clock.
Correct.
And then you received further information so that you could actually identify a time. Where did you receive that information from?
I'm going to allow that.
That was from Mr. Burgess's report.
And do you know where that information came from?
That came off the SD card, I believe, in the infotainment system.
Do you know when Mr. Burgess found the SD card on the infotainment system?
No, I'd have to go back to his report. But it was in it, this information was in his original report.
Based on the SD card information about when the car was turned on and off, how do you match that with the text stream data to get a time?
So when the car is turned on, that's approximately when the running clock starts in it. There may be as much as a 3-second delay in it, but that's approximately when the clock turns on. So this shows us when the stopwatch was started for the text stream data. So knowing that infotainment system has date and timestamps on it, so that ties it to a real world clock from GPS information. And so now we can, when that infotainment system turned on, it's very close in time to when the text stream data started recording data. That allows us to tie the two together.
The times that you're showing on this slide, does that relate to the first or second event on the text stream data, the first or second triggering event?
The first event.
Do you characterize the first event in any way?
I call it the 3-point turn.
In addition to the data you analyzed, was there any other information you saw that evidenced or supported that a 3-point turn occurred at the area depicted in your slide?
Right. We have a whole series of GPS data with heading angles, as well as a description that Ms. Reed gave in an interview.
The time that you have after you consider the SD card ignition on in the running time, what clock is that based on?
It's my understanding that's a clock in the infotainment system. And then we are ultimately trying to also tie it back to the clock on his cell phone.
Mr.
O'Keefe's cell phone, correct.
Do you have any understanding whether all devices have the exact same clock?
So it's my understanding they do not. In my discussions with Mr. Burgess, reading reports, that they can have, there can be as much as 30 seconds to a minute of variation.
Objection, Your Honor.
Sustained.
Have you ever heard the,
Strike, Your Honor, that answer.
Sure. Jurors disregard that answer.
have you ever heard the term variance before?
I have.
What do you understand that to be?
That means differences from the answer.
I'm sorry, differences from what?
From typically the correct answer. Like meaning that a given data point has variance in terms of how it's measured, when it's measured. So a different measurement device can have a different variance around the actual true number.
You mentioned on this slide a time of 12:23:38.
Correct.
In O'Keefe's cell phone data at .154, approximately 12:23:58.
Correct.
Is there a difference between the clock on the Lexus TechStream data and that of Mr. O'Keefe's iPhone?
There is.
When you developed the slide, did you have the benefit of more detailed information about data point 154?
I did not receive that until May 8th.
Did you later learn more information, more specific information?
Yes.
Okay. So I'd like to show an exhibit to Mr. Welcher that's already been admitted. It's 192A. Ms. Gilman, can we start with 192B? Dr. Welcher?
Yes, we'll call.
Dr. Welcher, if you could take us back to slide 30. And so we understand you mentioned there are two triggering events. Is this the first one or the second one?
It's the first one.
Is that the one you've labeled the 3-point turn?
Correct.
And where did that happen? What street?
Cedar Crest.
At this 3-point turn triggering event, there is a time in red, 12:23:38.
Correct.
Where is that time taken from?
That's coming from the cell phone of Mr. O'Keefe at .154.
Okay. And is there another time on there?
I do the math between those two.
Okay. Could you make that a little larger? Could you zoom in so we can
Sure.
see it better?
So there's an infotainment time of 12:36, I guess another time, that answer your question. Then we have,
The 12:36, what does that indicate? What's that relevant to?
that's when the text stream data basically turned on, plus or minus a little bit.
When you say the text stream, is that relative to when the car turned on?
Correct.
Okay.
So when the car turned on, then we add the time for the trigger. So what we have is we have data in the text stream that shows the speed, the position, the steering of the vehicle on that trigger. And so we're trying to match the timing and the description of what the vehicle was doing with the text stream, the infotainment, and the cell phone data.
Is the data that you analyzed regarding the speed, the direction, and the timing to determine whether this was consistent with a 3-point turn?
Yes.
Okay. Continue, please. And if you can enlarge that, because it's hard to see back here.
Sure is. Okay, so again, we are looking at event 1162-1. The information in blue is speed. It comes out of the text stream in kilometers an hour, converted to miles per hour, feet per second, looked at the total distance traveled, shift position. So in the text stream data, a shift position of 1 indicates you're in drive. A shift position of 2 indicates you're in reverse.
There's no zeros. What would a zero indicate?
0 is usually neutral, and I believe 3 is park. So there's also data on the acceleration of the vehicle. So basically, what is the effect of whatever you're doing in terms of stepping on the gas or not stepping on the gas? And then there's also information on the steering of the vehicle. So again, there's trigger, 5 seconds before, 5 seconds after. So over here, a positive number equals a leftward steer. So you can see we have in the forward velocity or forward motion in drive, goes forward with leftward steer, stops, shifts into reverse, and then continues with the rightward steer back.
Could you take us over to the left of that data? When you look at the number 1162-1 as an event, can a key cycle, or when a car is turned on, power ignition on until the point it's turned off, whatever amount of time, can it have more than one triggering event?
Yes, it can have lots of triggering events. In this case, it has 2. On a key cycle 1164, there's 11. On 1167, there's 10.
If you could move a little bit to the right on this, is there something you can see on here that caused the triggering event, some of the data?
Yes. So if you look at the triggering, the indication of what this trigger was, what you see is accelerator opening ratio, which is basically, you can think of it as how much you're stepping on the gas pedal. And so if it exceeds, in this case, 30% quicken time after shipping into reverse, that tells the system, hey, we might need to start recording this data. So what you can see, it went into reverse, and then within a very short amount of time, accelerator pedal went above that 30%. That's what caused the T, or the trigger, in the tech stream data.
The row next to the 31.5, engine RPM data, can you explain to us what that is?
Sure, that's how many revolutions per minute the engine's turning.
The more gas, is it generally the higher the RPM?
Correct. There's going to be a little lag. Your car doesn't move instantaneously. You have to step on the gas, then the RPMs go up, and then it starts going faster.
If you could explain to us the total distance and distance travel columns, how do you read that?
Sure. So we know the speed at various times. We know from this data that there is, you can see half a second between each one of these timestamps. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points at half a second. That's the 5 seconds of pre-crash data. So if you know you're going so many miles per hour, again, I converted it to feet per second. Feet per second, you're going so many feet per second for half a second, for example. You just multiply those two together and it tells you how far you went. So what I'm doing is looking at speed traveling during the interval, that's during this short time period, and then I add it all together here for total distance traveled.
You mentioned that when the data is captured, it's limited to 10 seconds. When we look at the top row of JBW vehicle speed MPH, it's 9.94. Is that 9.94 miles per hour?
It is.
Can we tell whether it was going faster or slower before this data?
We generally cannot. I mean, you might have some, it looks like it's slowing down, and then you see right here, this brake switch application. So you have two things relative to braking. You have a brake switch, which is simply whether the brake is on or off, just enough pressure to make the brake light come on. And then you have brake oil pressure, which gives you some idea of how much pressure is in the system, which is a rough indication for the braking. But then what you see here is the longitudinal acceleration or deceleration. This gives you some idea of how much the vehicle is speeding up or slowing down. So generally a minus sign is a slowing or accelerating in reverse.
And for the bottom of those columns, I'd ask you whether or not the beginning of the window, if you had any other information, is it the same situation for the end of that window that's captured?
Correct. So at the end of this window, you can see it's still going about 8.7 miles an hour when the trigger stopped. So after that trigger plus 5 seconds, the system said we no longer need to monitor it. Things have returned to an okay state. And so then it stops monitoring the system.
Based on your analysis and review and looking at this data, did you come to a conclusion to a reasonable degree of engineering certainty whether or when this event occurred as it is portrayed in the data?
Yes, I did.
And could you share with the jury, to a reasonable degree of engineering certainty, when did this occur?
So this, you want time-wise or location or both?
Start with location, then time.
So it happened on Cedar Crest. It happened between cell phone data points 154 and 155. and it's a 3-point turn on Cedar Crest. And it occurred, according to the text stream data, about 12 minutes, 23 seconds after the vehicle was turned on. So,
And do you have an understanding of the variance between the Lexus clock and Mr. O'Keefe's cell phone?
yes,
And what is that variance time?
21 to 29 seconds.
And so the Lexus clock at 21:23:38, what time would that put Mr. O'Keefe's cell phone?
Objection, Your Honor.
I'm going to see counsel at sidebar for just a minute, please.
Order the session, please be seated.
All right, so Mr. Brennan, you can continue. The objection's overruled.
Dr. Welcher, could you take us to slide 30? Could you zoom in a little bit on the right photograph and the text under the right? You were explaining to us the time relevance of 12:23:38. And could you tell us again, remind us, what is 12:23:38 referring to?
The 12:23:38 is syncing the text stream time to real world time. So we know how long the text stream is on, we know when the vehicle was turned on, so we're adding those two together. So if you add the 12:12:36 to, for example, 11 minutes, 2.8 seconds, or when the end of the trigger is, that gives you 12:23:38. So the end of the trigger in real world time, no longer in the running clock, is now 12:23:38,
Based on the infotainment clock?
based on the infotainment clock
And that's from the Lexus.
from Lexus.
Sustained.
And where's that from?
The Lexus.
Thank you. The 12:23:58 number, what's the significance of that?
So that is Mr. Keefe's cell phone data at point 154. Again, from the original data we had, just at 154 and 155, not the in-between points. So,
And at the bottom in parentheses, explain to us what that means.
sure, if you look at where the text stream math works out to be, 12:23:38.8, and compare that to 12:23:58, the difference between those two is 19.2 seconds.
The difference between which clocks?
Between what the text stream infotainment system would show compared to what point 154 on Mr. O'Keefe's cell phone is.
And based on new data, do you now have information about what the variance, the difference is between the clock on the Lexus infotainment and the clock on Mr. O'Keefe's cell phone?
Yes,
And what is that?
Objection, Your Honor.
I'm going to allow that.
you need to advance the text stream clock 21 to 29 seconds.
You need to advance it 21 to 29 seconds for why? Why do you need to do that?
Because the cell phone is ahead 21 to 29 seconds.
After you advance the text stream ahead 21 to 29 seconds, can you then compare the information, the time that's coming from the infotainment system Lexus to Mr. O'Keefe's cell phone from his iPhone?
Correct. That's where you need to have an apples to apples comparison. You need to get them on the same time clock.
Thank you. You can proceed.
So I think we left off here. So that's 1162-1. So what we have is we have the cell phone data, the original cell phone data on the right-hand side. And then from that text stream data, we have whether it's going forward, we have the speeds, and we have the steering angles. So from that information, we ran a simulation to show you what the text stream data means. This is what the 10 seconds of data is. Again, just because the simulation stopped, that's just where the text stream data ends. Again, as we showed you earlier, that the car's still moving, that's just the last data point we have. So what that text stream data shows is matching a 3-point turn on that Cedar Crest Street. So we have the vehicle motion, the timing data consistent with the interview statements about making a turn, 3-point turn.
Can you take us back to the data chart and show the 2 points that you just mentioned, the turning? Where's that reflected in the data?
Sure. So you can see
You have to enlarge that. I'm sorry, Doctor.
column N, that's the shift position. So that's looking, we start off going forward right here. And you can see at the start of the simulation, we're going about 9.94 miles an hour. And then as you start a 3-point turn, you generally start, in this case, if you're going to the left, with the left turn. So you can see we have this steering angle here, then the transmission. So again, we have the brake application. So you're coming in, but you're slowing down, and you get down to a speed of approximately 0. Shift into reverse, back up, and then start to turn the other direction as you're backing up. So again, you want the rear to go to the right, you turn the steering wheel to the right, right is negative, and then as you start to pull around and pull forward, you turn back to correct for the steering, and so that's what this shows. So again, if you put it all into a simulation program, the speeds, the shifting, the distance, keep in mind we only have that 10-second window of data, and the steering angle for that Lexus, that's what it indicates.
Can you enlarge the photograph on the right with the data points and explain to us the significance of that?
Sure. So again, what we're trying to do is we have the infotainment, we have a text stream. We're now trying to see how that correlates to Mr. O'Keefe's cell phone. So we had originally very coarse data points, 154 and 155. There's additional data points between here. So we're looking at how well does our predicted time compare to those two. So with the cell phone correction, you end up with the text stream data at 12:23:59 to 12:24:07. So that's actually right in between these two data points. And so we know 154 was closest, but it's on the right-hand side of the road. 155 is when it's turned around and heading back in a southerly direction. So the cell phone data corroborates the text stream timing data in conjunction with the infotainment system data.
Thank you. Please continue.
Okay, so we talked about 1162-1. That's the first trigger on the text stream. So we're going to go to 1162-2. So I've highlighted that in yellow. So we're now talking about the second trigger. So this is on the same ignition cycle. It's on ignition cycle 1162. We have that same continuous running clock, but we've now synced it to real world clocks. So instead of the running clock, we now have some information on the real world clock. So at this time, we know the ignition has been on for 19 minutes and 2 seconds. So at the trigger, 19 minutes and 2 seconds. And again, we have 5 seconds either side of that. So between 18 minutes, 57.6 seconds to 19 minutes, 7.5 seconds.
Could you enlarge that, please?
Which part?
That part where your arrow is. You were speaking about the clock. Could you explain that so the jury can see?
Sure. So again, this is continuous from when the time comes on. I just converted it to minutes and seconds here, so you can see how long it's been on. This is the mileage. These are the speeds over here. And this is some information on how far it traveled. Again, we have the plus minus on the steering. That gives us some information on the steering. Really, there's very little steering going on at this point. Slight leftward steer.
Dr. Welcher, did you determine how long after the first trigger, that 3-point turn, that this second trigger occurred?
Yes. The 3-point turn occurred about 8 minutes after.
You said the 3-point turn occurred
I'm
after...
sorry, this event, I misspoke. 11.2 occurred about 8 minutes after.
After the 3-point turn?
Correct.
Okay, thank you. Can you walk us through this data?
Sure. Okay. So we have the accelerometer data here. I've highlighted a shift from drive to neutral to reverse.
I'm sorry, let me zoom that in so we can see it.
Absolutely. We have information on the brake switch, brake oil pressure. We have the acceleration data here. And then from that information and using the acceleration data, calculating the speed at which it's backing up. The reason we have slightly different calculations here is we have some evidence that the wheel's slipping on the ground. So we need to use the accelerometer because the wheel speed is simply telling you the speed of the wheel. It's like if you're stationary burning rubber, the speedometer reads a certain speed, but you're not going anywhere. But the accelerometer tells you how much the vehicle's moving. So from all that information, we get information on how far the vehicle's traveled. We've done it in terms of total travel distance. We've done it relative to the start position.
I'm going to ask you to start on the columns on the left and take us through the information that you have regarding this second triggering event. So if you can scroll all the way to the left.
All the way to the left?
Yep. Okay. So the first column regarding time, could you remind us again what that is?
So again, that's the continuous running clock.
And the second column in blue?
That's where I take that time and convert it to what we more commonly use, minutes and seconds.
And now we have a key cycle event, different than the 3-point turn. What's the number?
So this is now 1162-2. So again, it's technically in the system the same key cycle. I've called it 1162-2.
And the red number next to it to the right?
That's the mileage. So it's actually at the same mileage as 1162-1. So we know, obviously, they're within the same mile.
If you could scroll over a couple of columns. From your data, can you tell during that event how far the Lexus traveled during that event?
Yes.
And how do you do that?
So we have accelerometer data. We have velocity data or speed data back here. I've corrected for what you see down here is, and I go through this on a later slide, but right here you can see a significant increase in RPMs, but yet the acceleration is dropping. So what that means is if your RPMs are going up and the speed's going up, that means you should be accelerating more. But what happens because the acceleration is dropping, that means what's actually happened is the wheel's slipping. So what I've done is I've used the accelerometer's data to calculate the speed once the vehicle is put into reverse. And once we know the speed, again, feet per second, we know every data point is half a second. So speed times time tells you how far you moved. Feet per second, feet divided by seconds times seconds gives you feet. That's how far you went. So you get how far you went in each interval, then you get the total distance traveled. And so this is relative to the start. So 0 is the start. The vehicle goes forward about 34 feet. Then you see it basically stops in this area here, then begins to back up and ends up backing a total of 53 back from where it originally started. So if you add 53 to 34, you get 87. So the total motion, 34 forward, 53 back, the Lexus moved 87 feet total.
Dr. Welcher, when you say the Lexus moved 83 feet total, is that according to the data, or is that the entirety of the movement of that Lexus?
No, that's just from when the data starts to when the data ends. So if you look at when the data starts, you can see that the vehicle is actually going 13.67 miles an hour. When the data stops, the vehicle is still going 23 miles an hour. And you can see,
I'm sorry.
you can still see that it's still at 74% throttle. So, this is 3/4 of full throttle in reverse.
So to start with the distance traveled, if you can go to the top, we see that the speed is 13.67. Is that where the data gets picked up?
That's where the first data point is. Again, the trigger is here. This is 5 seconds before the trigger.
Are you able to tell how fast or slow the vehicle is traveling before that data point of 5 seconds before the trigger?
No.
And likewise, on the bottom, the speed, at the end of the 10-second data points at 23.61, can you tell whether or not that speed stayed the same, increased, or decreased?
I mean, considering you're at 74% throttle, it likely increased. How much, I don't know. And you can see that up here, she's on the brake. Down here, she's not on the brake. And so she's not on the brake and at 74% throttle.
And what is the percentage of throttle that has to be initiated to cause a triggering event?
For a shift into rear and a rapid throttle application, it's 30%.
If you look at the next column over, if you can go to the top heading for the jury to see the engine RPM data, could you explain that?
Sure. Again, that's the engine RPMs. And so, as I mentioned, you have this jump in engine RPMs and a very dramatic jump in the reported speed of the vehicle. But when you look at the acceleration is actually dropping. So again, that's a telltale sign that the tire's spinning because the vehicle is not being accelerated. And so I've used the accelerometer data. Again, if you just, a process called integration, you integrate the accelerometer data, it will give you the velocity. So what I've done is, it's called piecewise integration to get the speed data that takes into account the tire slippage, and from there calculated the speed or to position at each interval going across the top here.
If I could stop you at your column that says JBW speed at each time step.
Yep.
If you go to the bottom, please. So does your data indicate that the speed is changing at the end of this 10-second event?
Objection, Your Honor.
Sustain.
Is the speed changing at the end of this event?
Yes.
How so?
Well, again, you can see it's increased about 2.7 miles per hour. And again, we know from what I already stated that that last time step, you're still at 74% throttle and you have 0 brake application.
Is it possible from the data to tell how far the Lexus went forward before it went in reverse in total as far as feet?
Not in total, no. We just have this 10-second window. I can tell you what it did during this 10-second window.
Is it possible to tell how far it continued after the data?
No.
The shift position changes from 1 to 0 to 2. Can you again explain to us what that means?
Sure. 1 is drive, 0 is neutral, 2 is reverse. And then brake switch status, again, a 1 is you're on the brake pedal, enough to activate the brake lights. 0 is you're off the brake pedal.
Each one of those indicators, 1, 0, 2, how much time is for each of those?
0.5 seconds.
So can you tell how long the Lexus was in neutral for?
So again, it only occurs at one time step. And again, there's a little timing issue, like we only have data every half second. You don't know exactly where in that time it was.
Okay, you can continue, Dr. Welcher.
Next slide or continue on this slide?
Unless there's something else you want to point out to the jury on this slide. You
No,
can
I'm
do
good.
the next.
So similarly, using this information to then try to tie it back to the cell phone data to make sure we have the real-time information. Again, this was written back in January before I got the additional information. So what you can see is, I'll zoom in. Again, we're now talking about trigger 1162.2. We know that that's 18 minutes that the vehicle has been on, 18 minutes, 57 seconds, 19 minutes, 2 seconds. This is the range. Again, the plus or minus 5 seconds. The 19 minutes, 2 seconds is when the trigger occurred. Infotainment system, adding those two together, 12:36, plus the 19:7.5 indicates the end of 1162-2 is at 12:31:43.
That 12:31:43, is it based on the Lexus clock from the infotainment system?
It is. It would need to be corrected to the O'Keefe cell phone data.
And when you reconcile that variance of 21.29 seconds, what is the time?
You end up with 12:32:04. So if you simply take this and add 21 seconds to it and add 29 seconds to it, so you get between 12:32:04 and 12:32:12.
When you reconcile the two clocks and you have that range of 12:32:04 to 12:32:14,
12:32:12.
I'm sorry, 12:32:12. Does that simply accommodate the window of data, but not before and after?
Correct. So, again, even on John's O'Keefe's cell phone, even within his cell phone, there's somewhere between 21 to 29 seconds difference on his cell phone. So even that one piece of instrumentation has some variance to it. So we know it's between 21 to 29 seconds at this approximate time. So this is taking into account that variance.
So the only time window that you have is based on the data, and that's reflected in the 12:32:04 to 12:32:12?
Sustained.
Is there any other window you can accommodate with the data you have other than that 10-second window?
Yes.
What's that?
So I was given information about a final lock event on the phone.
Let's stick with this window if we can.
Okay.
Since you only have 10 seconds of data, is it possible from the Lexus clock data to have a larger window than the 10-second window?
No, the text stream will only give you a 10-second window,
Okay.
but it doesn't tell the whole story because the vehicle's still moving.
Understood. Okay, continue, please.
So I have this other event, a lock event, and the information I was given that's at 12, it's 12:32:09. And so we have the text stream data ending at somewhere between 12:32:04 and 12:32:12, which puts this number right in the middle of that, more or less.
Continue.
Is this a good place to take a luncheon break? Certainly. Okay, so why don't we do that, Junior? So we'll take 45 minutes for lunch. And again, Dr. Wilson, you can just follow up.
Thank you, Your Honor. Thank you very much.
You are muted.
court is in session. Please be seated.
All right, Mr. Bonin.
Thank you, Ron. Dr. Welcher, when we left off, you had given us your opinion on this slide. Could we proceed to slide 35, please?
Slide 35.
I believe the next slide is 35. Okay. Now, when we look at this slide, I'm going to ask you to zoom in. If we can start from left to right, and we can identify each category as you discuss it and explain to us the importance of the columns.
So we already touched on this from left to right. The first column is the continuous running clock. Second column is where I converted it to minutes and seconds. You can see we're on trigger 1162.2. This is the second trigger. The particular boxes that are highlighted are where there's change. For example, in the upper right, when you're transitioning from drive to neutral to reverse. And then I already discussed this a little bit, but where the wheel's slipping, you can see you have high acceleration pedal application, increase in the RPMs. But when you look at the effects on the vehicle, you can see that it's accelerating less. So that's indicative of slippage of the wheels. And then I simply show at the bottom the math I use to derive all that. So again, we touched on most of this. It's the same slide you saw before, just to show how corrected for the speed.
If you could zoom in for a second, I want to ask you a question about the RPM column.
RPM column, go ahead.
If you could zoom in.
Oops.
You see in the last line, the last piece of data captured, the RPMs changed from 3,200 to 3,300.
Correct.
And the accelerator is fair to say, is that depressed? What's the way you characterize that?
Sustained.
How would you characterize 74? What does that mean?
I mean, it's 3/4 of full throttle. It's 74% of full throttle.
If above it's 74.5, it drops to 73.5 and then back to 74, why is the RPM higher than above?
So there's, again, this data is referred to as being asynchronous. You're reporting it at particular times, but the computer's scanning the network for the data. So it's not all on exactly the same time step. Not only that, but there's frequently, I'm sorry.
Sorry.
There frequently is a delay from when you step on the accelerator pedal to when that translates to increased RPM at the engine. It takes a little time to build it up or take it down.
Okay, thank you.
You're welcome. So similar to what we did on the first one, basically what we did is we took all the text stream data that we had, which includes the shifting, the forward, the reverse, and the steering. Again, there's a tiny bit of leftward steer, and put that into a simulation program where we're simulating what the Lexus will do. So we've taken into account the mechanical characteristics, the steering response of the Lexus. So this is to show what it represents on the left-hand side. So each one of these little hash marks, a different color, represents 10 feet. The red lines show the extent of motion. Remember what I said, initially pulled forward, then backed up, past its initial spot, and then went backwards further distance. So what this shows is where we simulated this in a program called HVE. So that's the vehicle, the Lexus pulling forward. And then it accelerated in reverse, past its initial starting position, and came to rest right there.
Doctor, when you say it came to rest there, do you have data that the defendant's Lexus stopped there?
No, it did not come to rest. I misspoke. That's where the text stream data ends, As you can see here, it's still going approximately 23 miles an hour when that ends.
You'll have to zoom in on that so the jury can see what you're referring to. Please.
So again, as I mentioned, the tech stream's taking a window of data. It doesn't take anything outside the window. You can see that when we account for the wheel slippage, that the vehicle at the time of the last data point, again, is at 74% throttle, 3,300 revolutions per minute, and is going backwards approximately 23.9 miles per hour. And you can see it's traveled a total distance backwards of 53 feet back from where it initially started, or if you consider where it pulled forward 34 feet and then backed up 53 feet, add those two together from the point it pulled all the way forward. So this is 10, 20, 35 forward. And then it'll go 10, 20, 30, 40, 53 back for a total of 87 feet. So from the maximum point it pulled forward to where it backed up, again, that was 34 feet forward, then a total of 53 back, total travel distance of 87 feet. So went all the way forward where it stopped, it then backed up 87 feet. And when the tech stream data stopped, it's still moving. It's still moving about 23 miles an hour, and you're still at 74% throttle and 3,300 revolutions per minute on the tachometer, RPM gauge.
We could turn the light on for a moment. Dr. Welcher, in your analysis of the data and the information you acquired and the evidence that you relied upon, did you come to some conclusions and opinions regarding the defendant's Lexus that evening?
I did.
As part of that opinion, you mentioned that you considered mileage to map distances as one way of mapping the location of the vehicle. Do you remember that?
I do.
If you could provide us with slide I believe it's slide 25. And could you widen the left-hand box a little bit? And you mentioned you measured or you ran information about distances between different routes?
Correct.
Specifically regarding Fairview to Meadows, the first box. Do you see that?
I do.
There are 3 different mileage numbers.
Yes.
And then there's streets to the left. Can you explain what's set out in that box?
Sure. It's basically 3 different routes you can go: Sherman Street, Pleasant Street, Washington, and Sherman Street.
When you considered the shortest route, 2.3 miles on Sherman Street, did you attempt to determine how long it would take to travel 2.3 miles, how fast the car would have to be moving or how slowly it would have to be moving to travel 2.3 miles in 4 minutes and 15 seconds?
Yes.
And what did you determine?
So to go 2.3 miles in 4 minutes and 15 seconds, you would need an average speed of 32.47 miles an hour.
What if you took the longest route, 2.8 miles, and you considered 2.8 miles in 4 minutes and 15 seconds? Did you make a determination?
I did.
Could you share that with the jury?
It's 39.5 miles per hour.
Is that what the average speed of the Lexus would need to be to travel that distance in that
Correct.
time? Now, turning to your study of these tech stream events, do you have an opinion, to a reasonable degree of engineering certainty, how many triggering events occurred? How many triggering events occurred in that ignition cycle 1162?
Objection, Your Honor.
I'm going to allow that.
In 1162, the tech stream recorded 2 triggering events.
And do you have an opinion as to the type of triggering event, the type of movement of the defendant's Lexus in those 2 triggering events?
I do.
Regarding the first triggering event, 1162-1, do you have an opinion, to a reasonable degree of engineering certainty, what type of event the first triggering event was?
Objection, Your Honor.
I'm going to allow that.
The actual trigger was excessive rearward acceleration. The event was during the course of a 3-point turn.
And do you have an opinion, to a reasonable degree of engineering certainty, the time between triggering event 1 and triggering event 2 in that cycle 1162?
Yes.
And could you share with the jury your opinion, to a reasonable degree of engineering certainty, the time between those 2 triggering events?
Approximately 8 minutes and 5 seconds.
And do you have an opinion, to a reasonable degree of engineering certainty, as to the type and triggering event of the second event, 1162-2?
I do.
And could you share with the jury your opinion, to a reasonable degree of engineering certainty, the type of event to that second triggering event?
Objection, Your Honor.
I'm going to allow it.
It's, again, the trigger event itself was a transition into reverse and then high throttle application. It's a forward motion followed by a lengthy high-speed rear impact, or rear motion.
Your Honor, I'm going to move to strike that portion of the answer.
Yes, I'm not going to highlight it.
Absolutely.
So get the answer again.
Do you like me to ask the question again, Your Honor?
Yes, Mr. Alessi, yes, right. I'll strike the previous answer. Go ahead and ask the question again.
Okay. Do you have an opinion, to a reasonable degree of engineering certainty, as to the nature of the second triggering event, 1162-2?
Just for the record, may I proceed?
Yep.
Yes.
Could you share your opinion with the jury?
The triggering event was high throttle opening in a transition to reverse. It's a forward motion followed by a higher speed rear motion. And at the end of the trigger event, you're still at 74% throttle.
Do you have an opinion, to a reasonable degree of engineering certainty, the entire distance captured in that 10-second window during the back maneuver, or 1162-2?
Do I have an opinion about it?
Do you have an opinion, to a reasonable degree of engineering certainty, about
Yes.
the entire distance that is captured in that 10-second window of the second triggering event, 1162-2?
So it obviously only captures what's going on during the trigger. It doesn't capture before or after the trigger.
Understood. Do you have an opinion as to just what is captured as far as the distance?
Yes,
And what is your opinion?
that it's 87 feet. So again, the initial forward motion is 34 feet, followed by it backing, crossing the initial point, and then backing up an additional 53 feet.
And finally, regarding this part of your analysis, do you have an opinion, to a reasonable degree of engineering certainty, as to whether the defendant's Lexus was decelerating, accelerating, or remaining the same at the end of that data captured at the triggering event 1162-2?
It was accelerating at 74% throttle.
In addition to your analysis of the tech stream data, one final question. Do you have an opinion, to a reasonable degree of engineering certainty, the relative time this backing maneuver occurred with the defendant's Lexus that you just spoke about?
Yes.
And could you share with the jury your opinion, to a reasonable degree of engineering certainty?
Sure. It matches the window of the cell phone data for Mr. O'Keefe that puts it in front of 34 Fairview. So the backing event occurred somewhere between 12/32/04 and 12/32/12. The
And
end
I
of the
want to
event.
turn to a different part of your study of this case.
Okay.
At some point, did you try to determine whether there was an intervening event that could have caused damage to the defendant's right rear taillight separate from a collision at Fairview?
I did.
Objection, Your Honor.
So the form of the question is to Vernon.
Okay. At some point, when you looked at the data and analyzed this case, did you consider including or excluding evidence, or did you analyze evidence to reach a conclusion, including or excluding whether there was an intervening event that caused damage to the defendant's Lexus right rear taillight?
Yes, I did.
When you started your analysis, what information or claim or evidence did you become aware of that you wanted to analyze to include or exclude as the cause of that damage?
Sure. So my approach to this case is three prongs. I'm looking at the downloads, the technical information. I'm looking at this backing incident, and then I'm looking at Mr. O'Keefe's injuries and how they relate to the events, potentially. So the second prong, which is looking at this data. So I had a Ring doorbell video showing Miss Reed backing the Lexus out of Mr. O'Keefe's residence at approximately 5 o'clock in the morning. And so we wanted to look at the backing activity and whether that contacting Mr. O'Keefe's vehicle, whether that was sufficient to cause, or what damage it could cause, and particularly was it sufficient to cause damage to the right rear tail light of the Lexus.